name is Carly Miller, and I'm at the University of Illinois in Urbana-Champaign. And I'd like to start out with discussing fossils today and the process of fossilization and why that's important. And one of the main things that we want to consider when we're thinking about evolution and how organisms have changed over geologic time is what is our evidence for that, and what is our evidence for the observations, the qualitative observations of how those organisms have changed over time. And one of the major pieces of evidence is physical fossils that you actually find in your backyard or in the field. And we want to start to get pretty specific about what are the types of fossils, what are the modes of preservation, which means how are those organisms actually preserved in the rock record, how that happens, what are the biases in the rock record, meaning are all the organisms actually represented equally throughout geologic time or in a specific sediment or something. And so to start out, just the definition of a fossil is just evidence of past life. So that could mean a skeleton, a footprint, coal, some sort of chemical trace, something like that. And all of those are evidence of life, and they are preserved generally in sedimentary rocks. And if you can find a fossil and start to think about it critically, we can actually deduce a lot of information about those organisms, how they lived, how they were represented over time, how they grew, how they died, all sorts of great information from a simple fossil specimen. So what I like to start with is just identifying the three types of fossils. So the first one is called a body fossil. A body fossil is just something that you can find that actually has the original material of that organism. So for example, we have a skeleton. So if you find a piece of a skeleton, a tiny little metacarpal, or the bridge of a nose or something like that, or a tooth, those are all examples of body fossils. And so that's the first type of fossil that you could identify. Secondly, there's a chemical fossil, which again, you don't find any actual original piece of the organism, but you find a chemical trace. And on Earth, that's carbon. So in this case, for example, coal is a great just piece of evidence that there was a lot of biomass, there was a lot of organic material present at that time that coal was made, basically. So that's an example of a chemical fossil, is coal. And so we're just looking some sort of a chemical signature, which again, a carbon signature that you find that is unusual and indicates the presence of a living organism. Lastly, we have a trace fossil. And I mentioned earlier that a footprint is a fossil. So you don't have an actual toe, you don't have the foot, but you have evidence that life was there, and you have a footprint. And so maybe a really exciting type of footprint is Sasquatch. No, should I say that? Evidence of Bigfoot. If we find an actual footprint of that would possibly be some good evidence. But more seriously, evidence of a dinosaur. If we can find a dinosaur track, that is evidence that a dinosaur lived. And so you can start piecing together what size was that animal, how did it run? Did it run? But we can start to figure out even its speed and how it ate. So even just from footprints. So and that again, that's called a trace fossil. So if you find a little slimy track in a some sort of a basin or something, and you see just a scrape or something that looks unusual to you, you might say something might have been dragging its body around here or dragging its tail, and that is a fossil if it's been preserved. So that again is evidence of life. So those are the three types of fossils, and as you go through the course and you're looking, we present you with different specimens to look at. You're going to want to start to identify these things as what category does this actually fall in? A body, a trace, or a chemical fossil. So here we have an example of a trace fossil. And so what you can start to observe about this particular specimen is that there's no real changes in color. There's no real obvious representation yet of an actual part of the body. And so what you might start to deduce is that this could be a track. This is a type of track or a trace. So this is a good example of a trace fossil. So thinking about how an organism is buried, what you might start to process in your mind is, well, what types of organisms are fossilized better than others? And what types of material are fossilized better than others? And so what we call this biases in the fossil record. And so what we want to consider here is, for example, you can think about comparing a worm, how a worm is fossilized, versus maybe how a shell is fossilized, or how some big bulky structure is fossilized, or perhaps how a delicate little skeleton, if a hummingbird's little skeleton is going to be fossilized well compared to a more simple organism. And so all these differences in organism structure and chemical composition and lifestyle, all those things affect how it is represented over geologic time in the fossil record. So, for example, one of the things you would consider is how the structure of the organism affects that. So, does it have hard parts or does it have soft parts? So which do you think would be fossilized better? I would say hard parts, right? So soft parts are generally, they can decompose quickly. If they're exposed to oxygen, that's going to decompose fairly quickly and be carried away by groundwater. But perhaps the bones or the shell or the exoskeleton, perhaps that is left behind more readily. And it is. So we have a better representation of those hard parts. And most of the time, you have to infer those soft parts unless you're really lucky. So another factor that affects a bias in the fossil record is the chemical composition of that organism. So for example, some organic materials are very resistant to decay. When we compare those to perhaps an inorganic material such as calcium carbonate, which is the composition of a skeleton. The calcium carbonate there is fairly easily dissolved versus maybe a more organic composition of a skeleton such as our bones. So that is something to consider, is what was that original chemical composition of that organism and how is that either more easily dissolved or does it resist decay and dissolution. So that's something that's going to be affecting how that organism is represented in the rock record. Okay, another one to consider when thinking about the modes of preservation is how robust is that organism? Is that organism? So is it, does it have big bones? If you think of an elephant, for a very obvious example, it probably has a very robust skeleton. It has to carry a lot of weight. It's very dense. It has to move those big muscles, and so you have a lot of calcification going on there. You have a robust skeleton. And if you think of maybe a bat to compare to mammals, if you think of a bat, that is a very delicate structure. Think of that wing. I mean, a very delicate structure there, tiny bones, probably filled, very porous. And so you would, if just for those two examples of just mammals even, how are those different types of skeletons going to be differently represented in the rock record? And so the answer to that is the more robust skeleton is generally preserved better, which makes logical sense. So the last thing to consider when thinking about how an organism is represented in the rock record is the number of parts that it's made of. So again, this should make logical sense to you, is that if you have a large number of pieces in your body, one might be scattered, your arm might fly off and be preserved elsewhere. And so that would be harder to reconstruct your entire body if those many parts were scattered. So versus maybe a shell or a bivalve that has two pieces, those two pieces, you have a better chance of finding those two pieces than 108 bones. No, is it 208? 208 bones in your body. So what we want to think about here is the number of bones, or number of parts, excuse me, that compose an organism. And so what you want to think about is that a larger number of pieces of an organism are harder to represent accurately in the rock record than an organism with maybe one or two or fewer pieces. So that's another introduction of bias into the fossil record. Another important usage of fossils and fossil assemblages, which is a collection of different fossils, often a different number of organisms, is the power of correlation. So you can look at fossils from a certain part of the world or a certain stratum, so a layer of rock or sedimentary rock, and you can travel to another area if it's in your backyard or if it's across the ocean in Africa or wherever, and you can look at those fossil assemblages and you can start to think about either the difference or the similarity in the organisms that you're finding in those regions. Were they actually juxtaposed right next to each other at one point, which perhaps with Pangea, we actually did have South America and Africa right next to each other, and so that could be a really logical geographical correlation you can make is, wow, these structures were actually right next to each other way back in geological time. And secondarily, you can start to think about how they relate to each other in time. And so if you see certain fossils living in maybe North America during a certain time in over geological time, and then you find them start to emerge maybe across an ocean again, you'll be able to inform the progression and evolution of that organism and how it was able to survive in different regions. So what we need to consider next is kind of the relevance of fossils. So if you find a specimen in your backyard, it's not just a pretty specimen. It actually has some very important uses when we're thinking about evolution and how the kind of the structure of the earth has changed over time, and how the representation of those organisms is both represented in the rock record and how we can interpret that. And so the primary usage for fossils is actually dating. So the geological timescale was actually sort of broken up or constructed by lining up the number of fossils, the number of organisms that we find in a certain age or a certain assemblage, and how maybe that organism started to decline and maybe go extinct, and then we have an emergence of another fossil that you see in another layer of sedimentary rock. And if that maybe becomes more robust, a more robust representation in the rock record, and then how maybe that declined over time. And so a lot of the major time points in the geological timescale are marked by these either mass extinction events, which were discovered by the representation of those organisms in the rock record. And so that's something that is really important with the usage of fossils, and when you consider a fossil, you want to think about how it lived, and we can track how organisms on Earth lived and changed and died and re-emerged over geologic time.